Okay, hello again. Bill Gillespie here, and today we're going to continue on talking about Bayesian modeling and simulation. And in particular, we're going to talk about some of the issues around trying to assess convergence, how to assess how many samples, whether you have enough, and maybe some idea of how many more you might need. And then we'll also talk a bit about how to how to implement hierarchical models in WinBUGS. And by hierarchical models, we're talking about things like nonlinear mixed effects models like we commonly use for population PK/PD problems. And how do we implement that in here? So we'll and go through a demo on that process. So let's get underway. Let's first talk a bit about assessing convergence and adequacy of sample sizes. Okay, we've got a process here where we're creating these Markov chains that begin at some starting points that may or may not be very representative of the target distribution. Consequence of both that convergence process and the fact that your initial estimates may be somewhat distant from the target distribution, target in this case being our posterior distribution of our parameters. Result of that is that the early samples may not be representative of our target distribution. And another thing, because we are dealing with a Markov chain here where each sample depends upon the previous sample, is pretty much by design that the MCMC samples within a chain are going to be autocorrelated. And consequences of that are, one, that inferences based upon MCMC samples are less precise than those that you would get from the same number of independent samples. And that autocorrelation can also influence the rate of convergence. In fact, it's usually the dominant thing in determining the rate of convergence. So in the extreme, if the correlation is very, very high in these things, convergence can be quite slow. So how do we deal with those? What are some of the things we have to do with? Well, first of all, because some of the initial samples may not be representative of the target, we're going to want to use a burn-in phase. Just the slang essentially for having a certain number of the iterations at the beginning you're going to discard because, again, they might not be representative of the target distribution. So we have a burn-in phase. Another thing that we're going to want to do is we're going to want to monitor for convergence to see, so that we can get some idea when it's achieved and thus know when to actually start collecting the samples and keeping them for making inferences. And the best way for doing that is to monitor convergence using multiple chains that have different starting points and seeing whether or not they appear to converge to a common distribution. Also, the individual chains, you'd like to see that if you look at those in history plots, in other words, history plots meaning you're looking at the values of the iterations where the values are on the y-axis and the iteration number is on the x-axis. You want the chain history plots to look more like straight horizontal fuzzy caterpillars than like wiggly snakes. And I put a couple of examples over here on the side for you here. The first one is an example of poor convergence in mixing, at least for a couple of the parameters. The most extreme one here is right here for sigma. In this model, notice that we have three chains and all three chains are completely distinct. They're clearly not describing the same distribution. So that's very strong evidence that convergence has not been achieved. Whether or not it ever will be achieved, I can't tell for certain. Theoretically, it probably would, but it could be a situation where the number of samples required for convergence may be very extreme and prohibitive in terms of the time it would take. We can't necessarily tell from that. So it's possible that more samples would be adequate to deal with it. it may be that you have to reconsider either the model itself or the way it's parameterized if you saw something like that. Similarly, we can look down here at right here, this parameter, the phi previous OAD here. Notice in this one that the three chains have more or less come together, so we don't have gross convergence problems, but we do have a lot of autocorrelation here. You've clearly got, if you look at any individual chain here, they're definitely wiggly snakes, which is an indication that even if they appear to have converged to the same distribution, the process here is happening, or the mixing here, if you like, is pretty slow. And again, this one you could probably get away with just doing a larger number of samples, and by larger in this case, probably 10 to 100 times the number of samples that are shown here would be necessary for something like this to give you adequate precision about the posterior distribution. Now contrast this with what we see down here for in this case it's a different, well, some of the parameters are the same. It's been, this is a slightly different model, so the parameterization's a little different. But you can see that with these, for most of them, you've got pretty good fuzzy caterpillars going on here. All of the chains are definitely bouncing around pretty much the same distribution. Probably the worst of them is this phi previous over OAD again. You can see a little bit of wiggly snake stuff going here. So if your inferences depend strongly upon that particular parameter, you might want to do a few more, somewhat more samples, somewhere on the order of 5 to 10 times more. But for the most part, this looks pretty clean. So that's just give you a handle on what poor convergence and mixing looks like versus good convergence and mixing. Now, my own opinion is that this approach, using the history plots, is probably the most reliable strategy for looking at convergence and mixing and getting some initial idea of whether you've got an adequate number of samples. There are a number of other convergence diagnostics that have been proposed in the literature. Probably the most commonly used one is the so-called Gelman-Rubin diagnostics, or the Gelman-Rubin-Brooks plots in here. Those are essentially ratios of the total variance across all of the chains to the within chain variance. So of course you can see with something like, say, this sigma plot up here, the within chain variance actually looks relatively small here. But if you were to look at the overall variance here, or even just look at the between chain variance, you can see that would be much larger than the within. So the number you would get here for the Gelman-Rubin-Brooks plot, or for the statistic here, would be considerably bigger than 1. Whereas for something like these, it's hard to distinguish chains pretty much. The distribution within a chain is very similar to the distribution across chains, so there you'd have values much closer to 1. And as I say here with the Gelman-Rubin-Brooks plots, you're looking for them to approach 1 for all the parameters of interest once the chains have converged. Actually, what I should probably do is I think I did show you an example of that last session, but why don't I go ahead and drag out one for you. Here, let me just shrink this guy. Oh, come on. Hopefully that's not going to be one. There we go. Let me, I think we had, for the solutions we did last time, I think we had examples of that. Let's see here. Yeah, I think I do. Just so you can see a Gelman-Rubin-Brooks plot here. Make this a bit bigger. Okay, let's scroll down. Okay, these are Gelman-Rubin-Brooks plots. And they have this number called the shrink factor, which again is essentially that ratio of the overall variance to the within chain variance. And these are actually the post burn-in samples here. Now, during the early part of this, you'll always see a lot of noise when you're first looking at this. But what you're really looking for is that this should, as we go out here towards the end of this, we should see this thing converging towards 1. Sort of a rule of thumb here is you probably want most of your parameters, or perhaps all, to be converging towards something less than 1.05. For that example we did, this was our hands-on one example. You can see this. By the way, I mentioned the statistics they get out of these are themselves have a distribution, essentially a posterior distribution as you're going along, so that you can get here they've plotted the median in 97.5 percentile. I've never really thought real hard about what I'm trying to see distinguish between these two things, but you're pretty much looking for both of them to approach 1. I suppose if things are really noisy, you might see something where the median seems to get there, but maybe the 97.5 percentile might be bouncing around and still being considerably more. Okay, but for all of these, you can pretty much see they're falling below. What do we got here? So, well, deviance isn't really the one we want to look at. Emax was one of the worst. Emax and EC50, you can notice they start out fairly high. They come down. It's actually difficult to tell exactly where we've landed here, but it's certainly close to 1. So we're probably in pretty good shape there. And ditto for EC50 and gamma. They're all fairly similar. They actually have a lot of autocorrelation in them, and that's why things are fairly large early on. And sigma is pretty clean. Actually, I'd have to go back. There must have been a little blip here, but keep in mind that look at the scale here. The scale is only going up to about 1.2, so these are all pretty low here. So things are pretty clean there. So you can look at that, but frankly, I would argue that when I come back up to our history plots, they pretty much tell the story already. I mean, you can see for sigma, it's particularly clean. Gamma, not too bad, but you can see some wiggly snake stuff going on, and Emax and EC50. So when I look at these, I see, well, they seem to be describing pretty much the same distribution when I look at the multiple chains for a given parameter, but I can see that particularly for Emax and EC50, and to some degree for gamma, there's still a lot of wiggly snake stuff going on. So if I wanted more precision in my parameter estimates, I probably want to do, if I had to throw in a number in this case, maybe about 10 times more samples to get good precision on these. Chances are what you'll get is you'll get tolerable precision here for things like a posterior mean or median, but if you're interested in having high precision for things like the bounds on a credible interval, you probably want to do more samples. Okay, let's go back to our presentation. Okay, yeah, I guess that's everything in that slide. So that was kind of the quick and dirty on how to deal with the convergence issues, or how to assess convergence issues. But then the part of the question here that I've already begun alluding to is, well, how many samples do I need? We've only sort of talked about maybe how many we need for how do we assess whether we've done enough to get convergence, but is that really enough to make the statistical inferences we're interested in? So that's where we're going on here. So of course the number of samples then is also going to depend upon the kind of inferences that I'm interested in. And the way we're going to talk about this is I'm going to start by talking about thinking about how many samples one would need if you were able to generate independent samples, which of course is not what you get from MCMC. They are correlated. But let's suppose we have independent samples. Let's start thinking about what's needed there, and then we'll talk about, okay, now how do we adjust that for when we're talking about correlated samples that we get from MCMC. So for independent samples, let's start talking about some types of parameters. Let's say the thing that we're going to be interested in, we're going to making inferences about, is going to be our posterior mean. And the posterior mean of some parameter theta, and right now we can think of it as a scalar parameter, that's estimated with a standard error then of is about what I called S sub theta over the square root of n, where that S sub theta is the standard deviation of our simulated values of our theta, and then n is the number of samples. So imagine we do some random samples then of our parameter theta, and we're going to use those random samples to estimate our mean. So in other words, we're going to take the samples, we're just going to sum them up and divide them by the number of samples to get that mean, to estimate it. Well, how accurate is that number relative to the true mean? And again, what we do is we take the standard deviation of our samples and divide by the square root of n. So that gives us our standard error for that. Another type of statistic we might be interested in might be a probability. Maybe we've done some sort of maybe logistic regression where the key quantity of interest in there is the probability that some particular event has occurred. How do we get a standard error for that? Well, that you can get in this case. So in the case of a posterior distribution, there we'd be talking about a posterior distribution consisting of a bunch of these. Where am I going here? Of a bunch of basically ones and zeros, and you calculate how many ones you get over the total number of samples you do to get this estimate of a probability, and you plug that probability in, times 1 minus that probability, divide by n, and take the square root of that, and that's going to be your standard error for that probability. So those are ways you could sort of calculate what would be standard errors for the accuracy of those point estimates you get. And a little more on that in a minute. Now in general, more samples are going to be required for estimating tail quantiles and probabilities than you need for central tendencies and probabilities that are near 0.5. So for example, if your inferences are almost all going to be based on a posterior mean or median, that requires fewer samples for good accuracy than if your inferences are going to depend on, say, a tail probability. And so you have to consider that. And we can illustrate that with an example here. So that keep in mind these are not schematics to tell you something universal about exactly how many samples, but they are just illustrating it for a particular case. So in this case, suppose our distribution of interest for theta is normal with a mean 10 and a standard deviation of 2. And what if we use simulation to estimate various features of that distribution? So let's say we're going to just randomly sample a bunch of values out of that, a bunch of thetas out of that value, and we want to estimate things like a mean of that distribution, a median, a fifth and a first percentile of that distribution, as well as maybe a set of probabilities. Here, the probability that the value is greater than 10. Well, keep in mind 10 is the mean, so that's a probability that's going to be around a half. Then we've got a probability that x is greater than 12, which is 1 standard deviation away. So I always forget what's 1 standard deviation. Is that somewhere around? That's somewhere around a, what is it, around a quartile? I forget now. And then we get one that's 2 standard deviations away. So that's about, that's getting out there around the 95th percentile. So that's getting into the tails. So these are different statistics that we can calculate from our samples, and those statistics, if we're working with posterior distributions, those statistics would be estimators then of the corresponding what do we want to call them, estimands, I guess, for our distribution. So the sample mean that we get here would be an estimator of our true mean mu here. Median, I guess, is also that in this case, since this is a symmetric distribution. And again, the 5th percentile of our samples would be an estimator of the 5th percentile then of this normal distribution, and so on. So what these pictures are doing is I've just generated a bunch of samples like that, and then I use bootstrapping to estimate standard errors due to simulation. And I did those bootstraps for a whole range of numbers of samples, going out to, I guess it's 10,000. So I did a whole 10,000, but then I did, for instance, a bootstrap standard error for if I only take 10 of those samples, 50, 100, and so on. So we can sort of see how accurate these these sample statistics are taken from those simulated values. I've plotted this both in terms of relative standard error for the statistic as well as for the absolute. Let's use just the left-hand side one for now and just talk about the relative standard error. And let's suppose that for each one of these statistics, I'd like to figure out how many samples I need to get about a 1% standard error in these things. So that 1% standard error then would correspond to right here. So you can see that's between, this is a 0.5% and 2%. So this horizontal line right here represents a 1% standard error. So let's talk about the mean first. Okay, the mean is this black curve right here, and we can see that, in fact, you can sort of look at things. So for example, for a 5% error, it looks like I only need about 20 samples to get a 5% error for this case, and here, but to get a 1%, I've got to come over here, and we're about here, so I'm somewhere less than 500. So let's say roughly 500 samples I would need to get to be assured of having around a 1% standard error in my estimated mean, posterior mean here. For the median, which is the red curve here, it's pretty similar. It's in the same neighborhood on that, and that's pretty much what I would expect. But now suppose I want to start asking questions that are getting more into the tails. And in particular, let's start with the 5th percentile here. Well, here that's the green one right here. Notice the green one here doesn't cross our line here till we get to about 5,000 samples. So if I wanted to make an inference that depended upon that percentile here, then I've got to pull at least on the order of 5,000 samples to do that. Then if we go out further to the 1st percentile, and I unfortunately wrote over that here, but that's the dark blue curve here. Notice that that's going out here to somewhere in the 10,000 or more neighborhood in order to get adequate precision at the 1st percentile. So again, you can see that how those work. Now suppose that I want to calculate probabilities with a 1% error in here, and notice even for the central one here, where I want to know a probability that should be about 50%. That's the sort of blue or cyan dash curve here, and that's coming down right here. Again, that's roughly around, still requires around 10,000 in order to get that with a 1% error. If I take us out one standard deviation outwards here, that doesn't even hit it within the scale of here, if I had to guess. So that's probably going to be out here somewhere around the 50,000 neighborhood in order to get that with 1% error. Of course, to be fair, you're also talking about a quantity. Since we're talking about a probability that's going to be around, what is that going to be around? Around point, what do we think it is? Around 0.2, something like that. We're also dealing with a smaller number in here. And then at the extreme here, when we want to calculate, say, a probability here, which is 2 standard deviations out, here. That one's going, I don't know exactly where that lands, but we're probably talking, I don't know, must be somewhere around 100,000 plus before that one crossed the 1% boundary. Even to get that with 5% error, we're talking more than 10,000 samples to calculate that. So my point is not that those numbers I just gave you universally apply to these particular statistics for any problem, but they just illustrate for this case, what will generalize is this notion that these that inferences related to things that are measures of central tendency will require fewer samples than things that pertain to tail probabilities and tail quantiles here. So that's something you need to keep in mind. So for example, if let's say you're doing a clinical trial, you're going to analyze it using a Bayesian method, and you are going to and let's say you're going to let's say stop the trial if the posterior probability of success, however that success is measured for the given treatment, is say less than 5%. So now you're talking about a probability that's in the tail regions there, and if you want to determine that with high precision, because of the fact that your whole program is depending very heavily on it, you're going to have to do quite a few samples to estimate that. Okay, now what I just talked about was for a case where we were talking about independent samples. And in the world of MCMC, we don't have independent samples. We have correlated samples. And what do we have to do with that? Well, it is possible that with a given set of MCMC samples, there are methods to estimate an equivalent number of independent samples, or put another way, a number of independent samples that would give you, how do I put this? It would be the number of independent samples that would give you the same precision as the MCMC samples you've generated. And usually that equivalent number of independent samples is going to be somewhat less than the number of MCMC samples you've generated. You can also get an estimate of the standard error in the estimated posterior mean. And there's a few tools out there to help you with that. In particular, we'll be making use of the ones that I mentioned here. There's a couple of R functions. There's one called effective size and another one called summary MCMC that's in the CODA package that we use. And in fact, if you go back to the example we did, I actually provide the consequences of these. If you look in the parameter plot table function that I give you in the BUGS tools R script, it makes use of both of these functions for generating those quantities in there. And I put them in the plot. So you'll see, for example, I'm trying to remember the names I used in the table. Maybe we should actually go there just to show you here. So let's take a look at the table. Actually, we can do it this way. Where's the table there? That's right there. We can do it this way here, although it's kind of tiny. Let me open it up here so you can actually see it. Take a second for oh, I just realized it's not opening the thing I wanted it to open. Let's do Excel instead here. Take a minute for Excel to kick up here. Okay, Excel, you can do it anytime. Okay, well, while it's trying to get started here, I was just going to show you where those show up in the results and the way that we're going to be working with these and the way I did it in the example I showed you for our, well, both for the linear example as well as what we did last for our last lab session. But the point where I'm going to be taking you here, oh, is it opening? Come on. Rather not interrupt the next issue here if we can avoid it. There we go. Let's make it a little bigger. Okay, so when I produce these tables with parameter plot table, there's a couple of columns here of interest. This thing that's called time series SE, that's the standard error in the posterior mean estimate here, adjusted for autocorrelation, and that's the thing which is, let's go back here, that's the thing which uses that comes out of the summary.mcmc run. Actually, summary.mcmc produces a bunch of other statistics too, but in particular it produces an estimate of the standard error adjusted for the autocorrelation. And then here is our effective N over here. And I'm trying to remember for the example that we did, how many did we do here? I think we have 3,000 samples? I think so. And you can see here that the amount of autocorrelation in Emax, EC50, and Gamma is actually pretty large, such that even though we did like 3,000 samples, only we get back, what, roughly 5 in the case of Emax and EC50. The effective number or the equivalent number of independent samples is only about 5% of that. So that's gives you some idea of how extreme the autocorrelation can influence the effective number of samples or the equivalent number of independent samples. Okay, let's get back here. Okay, so the point I was going to make is, given that, you can sort of draw on guidance based on independent samples to decide whether you've generated enough for the given case you've wanted. So we discussed the underlying principles here for evaluating how many independent samples are needed for different types of inferences and different types of statistics from your posterior distribution. And then we've got an adjustment we can do given our autocorrelated samples and try and assess what we need based upon that. In particular, I tend to look pretty heavily at that, at the equivalent number of independent samples, and use that pretty strongly as guidance on what I need here. So if I have some idea that, hey, I'm working with tail probabilities that I probably need on the order of tens to hundreds of thousands of samples to get adequate precision there, then I will tend to look at my equivalent number of independent samples, and if I've done a certain number of samples, I look at that value, I say, okay, is that what I needed? If it's not, I can scale things up accordingly. So for example, what we just looked at here, where we were seeing on the order of around 150, where the equivalent number of independent samples was around 150, and let's say I think, well, I'm probably going to need more like at least 500 to get the kind of precision I want maybe in the posterior means. Well, that tells me, okay, did 150 in order to get that up to 500, I'm going to have to do, roughly 3 times more. In fact, what is it? A little more than 3 times more samples than I originally did. So if my original samples were, say, 10,000 per chain for 3 chains, well, it looks like I better do, more like, 30 to 40,000 per chain for 3 chains in order to get adequate precision. So that's what I mean by this. I also giving you a pointer here. There's a whole lot of literature on dealing with this in a far more rigorous and comprehensive fashion, and I'm pointing you to the Robert and Casella book, or books actually. There's a pair of them there that I cite in the back of the slide. So if you're really interested in digging hard into that, that's the place to start. Okay, what button did I just push? Oh, that was very clever of me. I just pushed the N button instead of the page button. Okay, let's get back where we wanted to be. Okay, so that's the topic that's pretty much the coverage I was going to do then about the convergence and numbers of samples. Let's move on to the next topic, which is how do we program, hierarchical or population models using bugs. So this probably has more to do with the plumbing in bugs than it does with Bayesian stuff per se, but we'll need this as a tool when we move forward. So let's start by considering the usual case we encounter in population modeling, where we want to model 2 levels of variability. We'll have our usual residual variability, but in addition we'll have some inter-individual variability that we need to describe. And let's say that, and let's structure our data. In fact, we'll structure it, for those of you used to using non-mem, we'll structure that very much like non-mem. So we'll have a data set where the bulk of it basically looks like a non-mem data set, in the sense that it's going to consist of a set of equal length vectors, which is equivalent to a square table really, where that will include, for example, data values for each observation. That'll be like one of those vectors. Then there will be some individual identifier, like the ID variable in non-mem, but we're going to put a particular restriction on it, and that is that it has to be a consecutive sequence of integers beginning at 1, because we're going to take advantage of that as an index within our model. And if the if your initial data set doesn't have that, it's fairly simple to create one. So if you've got like a non-mem data set for ID, you've got a bunch of values which are unique but not a sequential set of integers. It's pretty easy to construct we'll just create basically another column that will be such a sequence of integers. And then you may have a bunch of covariates in there, and in particular we'll, for the context we're working in, typically we'll have dose and time in there. And then in addition, your data set may include a bunch of constants, things like how many observations there are, how many patients. You might include, for example, the parameters for prior distributions and things like that as part of your data set. So let's start there. Let's take an example as a way to describe how to do this. What I'm going to do is take, in this case, we're actually going to do a meta-analysis where I'm going to have sample mean responses from 5 different clinical trials. So in this case, our individuals, if you like, will not be individual people. They will be individual clinical trials in here. And we're going to do this, and we're going to use that to do a meta-analysis where the inter-trial differences then are going to be modeled as random. So we've got inter-trial variation as well as our residual variation. The plot on the left is showing our response versus dose here. I don't know why this is sort of blinded. As I recall, I think this is just percent change in HDL. I'm sorry, in LDL following, I forget which statin. This corresponds to one of the statins. I forget which one. So these are a bunch of studies. You can see some of them are dose response studies in here. So you've got, a collection of placebo values here, and then various doses going up. And here's a tabular form of the data that's plotted on the left. So you can see we've got different columns. We've got study ID here, which I've already shown here is a sequence of integers beginning at 1, 2, 3, 4, and 5. Then we've got our dependent variable, or our independent variable here is going to be dose. We're also going to have to adjust for the fact that we have different sample sizes for these sample means. So I've got an n here, the number of patients contributing to the sample means, and I guess these are made up numbers in this case, since these are all nice round numbers. And then our mean responses here are shown right here. Again, those are the same numbers plotted on the left. So that's our data set. And the model we're going to propose for this is going to be a simple Emacs model, where we've got log normal residual variation. So we've got, for our likelihood then, we've got our log of our effect here is going to be normal with some mean here, log of E hat. And our variance here has to be sample size adjusted, since we're talking about means in this case. So it's going to be a sigma squared divided by the sample size for each one of those sample means. Then our E hat here is going to be our Emacs model. So we've got some intercept here, and do we even need an intercept in this example? Yeah, I guess we do. We've got an intercept here, and then we've got our simple Emacs model with no hill parameter in here. And in addition, we're going to put inter-trial variation on both the baseline and the Emacs. And in this case, I'll describe them both as log normal. So we've got our log of E0 is going to be normal with some mean mu E0 and some variance omega squared E0. And same deal over here for Emacs here. We've got a bunch of weakly informative priors stuck on these things then. So we've got our means here for E0 and Emacs are both centered at, keep in mind those mu's are for the log of those quantities, so they're centered at 0 with a variance of 10 to the 4th, or put another way, a standard deviation of 100. And then for our ED50 here, same deal, our log of ED50. Sigma will make uniform 0, 10 to the 4th. And then, in fact, we'll do the same thing all the way across on all the variances here. We'll just make them all uniform 0, 10 to the 4th for our prior distributions. So they're all very weakly informative. That's what we're going to do. And how do we implement that in WinBUGS? Well, the first thing we need to do is keep in mind that these things here, notice the indexing I've done here. So think of this as the ith, let's see, this would be the ith treatment arm and the jth trial. So the inter-trial variation then is only going to be sampled once per trial. So each of these, the log E0J, you only generate one value for each trial, and the Emacs J, you generate one value for each trial. So we have to figure out how in bugs we're going to do that once per trial, whereas the observations here are going over all the treatment arms and all the trials in here. And the trick for doing that is to split it into two loops within bugs. And the first loop I'll show you will be just looping over the trials to generate our random effects. So we're showing that, and I'll show you the specifics here. We'll actually do it as a demo, but these things are in your USB drive. There's a dose response 1 directory in there that will contain the bugs model under the name doseresponse1.txt and an R script, doseresponse1.r. So First step, so we're going to model our intertrial variation, and we do that by putting it within a loop that loops over all of our studies. So you can see the way this is written, n study has to be defined somewhere, probably in the data set. And in our case, that's going to be a 5. So we need to generate our intertrial variation in both our Emax and our E0. We're doing log normal distributions, and as I think I had commented before, I've usually found it more successful to use the transformed variables like this rather than using the DL norm distribution within BUGS. For whatever reason, the DL norm seems to be sampled differently, and I usually find it runs slower. So we're going to do it again this way. So I've got log.emax representing the log of Emax is going to be distributed normally with some mean and some precision in here. And same deal for log E0, and then I just convert back here. So I take those log quantities here and generate the trial specific values of Emax and E0. Okay, so again, we're looping over the studies here to generate our random effects. So we've got that. Then we're going to have a second loop that's going to loop over all of the treatment arms for all of the studies. So n arm then is going through all of them. So if we go back to our data set, for example, if you count these up, what do we got here? 1, 2, 3, 4, 7, 9, 12, 16. I think we have 16 rows here. So our n arm would be 16 in this case. So we're gonna go over all of those treatment arms. We need to, well, I guess our main where to go here? Oh, I forgot about that trick. So we've got our Emax model here is being generated, and this is where we have the little trick we have. Now notice this is a separate loop from the other loop. They're not nested within one another. By the way, notice I used I for both of them. That's arbitrary. You can use whatever you want. You can use the same name or a different name. If they're not nested within each other, then the I in this loop has nothing to do with the I in the other loop. They're separate. But if for readability you find it better to use different names, you can do that, no problem. Anyway, so we're going from, so the I now represents an arm. So the expected value, or the mean for our response, actually it's the mean for the log of the response in this case. No, I'm sorry, it's the mean for the, actually the median for the response here. So we've got our Emax function, pretty much what you'd expect, E0 plus Emax times dose over ED50 plus dose. But the thing that's the trick here for dealing with picking off the appropriate E0 and Emax is we have the index here on E0, for example, is not I, it's study I. So we've got nested indexing here, where study is actually one of the vectors in our data set. So for example, let's go back up to our data set. The study we're talking about is going to contain one of these values from 1 to 5, and that's actually passed as part of our data in here. So that's actually an item, that's something in our data that we pass in. So it's going to take, so for the ith treatment arm, it'll pick up the appropriate study indicator. In fact, let's go back again. Sorry for jumping back and forth too much. So suppose that the I is, I don't know, let's suppose it's 8. Okay, that would be 1, 2, 3, 4, 5, 6, 7, 8. So that would be this row right here. So that would be the 8th row, and so I is 8. That means that study I would be 3 in this case. So it would be picking off the third E0 that was generated in that previous loop. Same thing is true here for the Emax. It will pick off the correct one for that. So that's the trick for dealing with the hierarchy here that we have between studies and individuals, basically. So they generate that to get this in terms of the quantity we need, because we're going to be dealing with a log transform. I take the log of that, to get my mu response here. Another thing is for our tau that we're going to be using here, in other words, our precision in our for our residual variation. Recall again, sorry, we have to do this sample size adjustment here. Now we've got the variance divided by n, but for bugs we have to parameterize it in terms of precision, so it has to be in terms of the reciprocal of the variance. In other words, it's going to be n over sigma squared that we're going to be putting in there. Okay, but the way I've parameterized this is we've got like a precision, or this would be, this tau dot RESP would be our 1 over sigma squared. So I multiply that by n, and the result is equivalent then to n over sigma squared to get the appropriate tau for this particular treatment arm. And then we finally come down to our likelihood here. So the log of our response then is going to be normal with some mean and precision, and we've generated all those up top here. I did one extra little trick here that frankly I seldom use, but I put it in here just to point up a feature that's in WinBUGS. If, let's suppose the data set doesn't have the log transform value in it, suppose instead it's in terms of on the original scale for our response, but I want to use a log transform, I want to use a log normal distribution for that. Well, this is one trick you can do for doing that, is you can actually do the transformation first and then put that transform value on the left hand side of the likelihood. However, this has some limitations that causes me to usually stay away from it. One is it's only applicable to a limited number of transformations. As I recall, I think it's limited to log, logit, and complementary log, something like that. I won't swear that that's the exact limit. I'd have to look at the documentation, but it's limited that way. The other limitation is you can't use it if any of these RESP values are missing. And there's a lot of situations we encounter where we'll have some missing values in it. So I usually don't do this. I usually log transform the data and just work with it directly in the likelihood. But I just wanted to make you aware that this feature does exist, which can occasionally be handy. So we've done that. Then I just have a whole bunch of priors in here, and these are nothing more than what I showed, and you can tie them back. Recall I said I had the mu E max was normal 0, 10 to the 4th, where 10 to the 4th was the variance, but now we've got to put it in terms of a precision, so it's 10 to the minus 4 in there. So I do that for our Emax or E0 and for the log of the ED50. Then I convert them, back transform all of those, and then recall all of our standard deviations I put in terms of uniforms that go from 0 to 10 to the 4th, and that's what we've got here. And then I convert all of those to precisions. Trying to remember why I did this. I also converted them to some of these things I labeled as converted them to CVs on some of these too. Why did I do that? I forget. Actually, it's unnecessary, come to think of it, because that's the same as the originals. But anyway, we can ignore the CVs on this. So that's actually the whole thing. Let's see, what did I do next here? Okay, well, let's actually, rather than show you the results here, let's actually go ahead and do this process. Let me take us to Windows World here. Hopefully that's behaving today. Or not. Oh, I think I didn't push the right button. That would help. Okay, so again, that's going to be in this dose response 1 folder in here. we've got our model in here. Let's go ahead and why don't we go ahead and open it up in WinBUGS here. I can show you the pieces. So we've got our let's see, it's bringing our model here. So I've actually added a little bit. Actually, let me show you this one first, the one I labeled as bare bones, because what I showed you in the slides is what we're looking at here. Let me widen it a little bit. Oh, it didn't. Do it. Yeah, I was just unwrapping some things there. So what I'm showing here is actually the same thing I showed you on the slides here. So you can see our loop here for our intertrial variation, so where we generate the random effects for our trial specific parameters for Emax and E0, and then here we loop over the arms to describe our likelihood corresponding to our sample means for all the treatment arms. And as we scroll down, then we've got all the prior distributions that we just looked at. So that's exactly what we had there. Now the one thing I haven't done here is put in anything in order to get some posterior predictions that we're likely to want to use for both inferences and for model checking in here. So let's go ahead and show you the more complete. Actually, I think it's still here, isn't it? Yep. Let me enlarge that one too. And okay. And what I've done here is I've added some pieces, and this is where I have to introduce another sort of new concept in terms of our predictions here. When we're dealing with a hierarchical model like this, there's actually at least two classes of predictions that we're likely to be interested in. And for those of you used to using non-mem, you should be able to identify with this to some degree, because they're two that are analogous to what we commonly term individual and population predictions in working with population modeling, and the same dichotomy occurs here. So the first type of prediction we'll talk about is what we could call an individual prediction, and that is shown. Let's see which one is okay. That one is shown right here, and I've used the sort of the modifier on this. Remember, this up here. Right here is our original likelihood in here. Right here is for our predictions of for our responses. These are for my individual predictions. And by individual predictions, I mean we're talking about predicting what you could hypothetically think of as being new observations in the same studies in here. So they would be new observations. It would be like, let's suppose you somehow were able to magically replicate, the same patients in the same studies and do the same treatment over again within it. These would be predictions for those cases. So in particular, they're conditioned on the study-specific random effects in this case. So those would be our so-called individual predictions in this. And if all you do for that is I use, see the likelihood here, I just repeat that and just put a different name on the left-hand side. And that gives me my individual predictions that represent that, that inference of, okay, well, what if I did the same experiment in the same patients in the same study over again? What would I predict would happen? And so I do that, and then this is just doing the back conversion to get rid of the log transform here. Okay, now the other class of prediction would be, okay, what if I want to make inferences about what would happen if I did a new study. So it'd be a new study, a new set of patients, same treatment. So let's suppose we basically replicate the same studies, studies with the same designs, but with new patients, maybe even in new places in here. So they really are new studies, but with the same design as the previous studies. That's going to be what our population predictions are in this case. And what we have to do there is we not only have to generate sort of new residual variation on here, we also have to generate new random effects that represent these hypothetical new studies. So I also have to do some work up here in, okay, where'd my cursor go? There it is. Up in our loop that goes over studies, I basically take my original random effects generation that I do here, and I do it again here. So this is actually identical to the one above, but I've renamed what's on the left-hand side. Excuse me. In here. So you notice I've stuck a dot pred on everything here on the left-hand side. So those would be then simulated or predicted values for Emax and E0 for these hypothetical new studies, and then I use those values down here within the loop that goes over arms to generate new values here. Let's see here. Okay, so we've got, again, your basic likelihood statement is really occurring right here, where I get the log of the response in here, and that's going to depend upon this mean here, this mu response, but I've got dot pred on it, and that value is generated, where we got it here, okay, sort of two steps here. I had to take a log transform here, which ties back up to right here, which again is our Emax model, but our Emax model where the E0 and the Emax are the ones that we called E0 pred and Emax pred in this case, which are the values that we simulated for these hypothetical new studies. But we're going to, again, in here, in order to use it for model checking, we've simulated the same number of studies with the same design. In other words, same treatment arms and the same numbers of individuals in order to do our model checking, or model, looking at the quality of fit here when we do our posterior predictive checking. So that's an important notion here. Again, we've got our individual predictions going on that I use the .cond for conditional. The reason I use .cond, I don't know if it's an ideal name, but it's because it's conditional on the individual random effects for the same trials that were used for analyzing the data, whereas the preds here are not conditioned on those. They're conditioned on values of our random effects for hypothetical new. They're basically simulated random effects rather than fitted random effects in this case. Okay, so we're going to generate plots for both of those things. Let me go ahead and pull up the corresponding R script for this. Okay, let's open that up. My computer. Okay, C250 dose response 1. There we go, dose response R. Okay, this is you'll find it to be very similar to the ones we did both for the linear 1B example and when we did your last homework example. The bulk of this is very much the same. Of course, we've got a different model name now. We call dose response 1 in here. I'm going to come down. There are a few things I've got going on. Let's see, what do we got? Excuse me. Okay, one thing that's different here is I'm showing the process of reading in the data. That's what I didn't show you. It didn't show you the data set. Let me actually do that you've kind of seen it in the when we were looking. You've seen the format of it just shown as a table on the slides, but let's actually look at the data set. In its somewhat raw form. Let me go ahead and pull it up in Excel again here. Okay, bigger. So you can see here it's now actually under the hood it's a comma delimited set of values here. So if we were to look at it completely raw here, I just open it up with just text edit here or something here, just so you can see it in its completely raw format here. Come on, enlarge. Okay, so in its raw format, you can see it's actually a comma delimited set that I've got it in right now. So you got your study, you've got the header here, and then like here you've got the study, comma, the dose, which is 0 for the first one, number of samples 40, and 2.02 is the response. So, and then you can see it done up in Excel here. So that's the data set we're going to read in. The easiest way to read that in is what we've got right here, where I'm using, well, in this case I used read table. Actually, I just realized, I guess I wrote this script a while back. Actually, the way I would probably write it now is I'd actually probably say read CSV like that, and if I say read CSV, I can get rid of the rest of this junk. That'll pretty well take care of it right there. The only other thing I might do in here, just to be on the safe side, is I might put an as is equals true here, just so it doesn't convert things to factors that I don't want to be factors. You could also use, strings as factors equals false. It should work there. So that's typically how I would read in such a file like that. So that should take care of that. And in fact, we can even show, why don't I sort of show the process down to there. Let me just go ahead and run that. Okay, hopefully I didn't mess up in my choice of variables there. If I was to look at our X data now, you can see we got exactly what we wanted here. We've got our study, dose, and response here in the format we need them. So we've got our data there. Creating the BUGS data format is pretty trivial at this point for this example. For the number of arms in here, it's just the number of rows in our data frame that we created there. So you can see I just generated that by taking n row of the data frame. The number of studies in here, the way I did that is I first of all find out how many unique values of X data $study we have, in other words the unique values in the first column, and then just get the length of that, and that'll tell me how many studies I had, and it should return a value of 5. And then the rest of it is just grabbing the different columns. So study is going to be that first column, dose the next one, and the next one, and response the last one. So that's all there is to creating the data set for the different pieces we had. Recalling that, where are we here? Just making sure we've got basically all the pieces here for our data. I won't worry about it. Okay, now we need to create initial estimates. What do we need initial estimates for? The best clue for that is to come down to our prior distributions here. We need pretty much anything that has a squiggle in it down here in the prior distributions we need to provide initial estimates for. So you can see we need them for this right here for our, so we need them for mu Emax, mu E0, log ED50. Let's see, got arrows. Okay, here's some more squiggles right here. And we need them for omega Emax, omega E0, and sigma. So those are the standard deviations for those. So we need those guys. So, And I'm showing you two different ways you can do it. I mentioned the first way here, but didn't actually do one before, so this is just illustrating it for you. So one approach would be to explicitly specify initial estimates as a list of lists, where each one of the internal lists is a single set of initial estimates. So that's what I've done here. So I've got bugs in it equals an overall list, an umbrella list, but then inside of it I've got lists which provide all of the initial estimates I need. And I see I've made an error of some kind here on top. This wouldn't actually work. Which one is it that I'm missing? I've got omega, I'm missing sigma, right? Is that what I called it? Yeah, I don't know why that's not there. This actually needs to be sigma equals there. So if you actually tried to run that particular one, it wouldn't have worked. I guess that's probably why I didn't find it before, because I don't actually use that one. I use the second case that I show you, which is the method that I showed you before, which is to specify initial estimates with a function that generates a list, where within the list I use random number generation to generate the individual components that I want, and that's generally what I use and what would actually have been used in this case. So got that here. So for instance, for mu Emax, I'm taking, recall that mu Emax is actually the mean of the log of our Emax. So that's like our population, the population mean log of Emax. So we generate R norm 1, and oh, I see what I did here. I also did I actually did an initial fit. I did a nonlinear regression here to get some initial ideas on what some of these parameters would be, and then I pull out the corresponding values. So here I use GNLS to do a nonlinear regression on that. It's just a least squares regression, so it's crude. It doesn't appropriately take into account the fact that we've got different sample sizes or anything. It's a very crude fit. And then I pull out the standard errors that correspond to the various parameter estimates in here. And so I'm putting in here, for example, for mu Emax, I've in here take the log of the estimated Emax I got from up there, and then I take the standard error for that thing, and actually what I do is I take it's basically like a CV. I take the standard error divided by the parameter and multiply that by 4 to get sort of an over-dispersed set of values out of this thing. And I do the same thing for E0 and for ED50 are taken from that. In the case of the variances, well, there's actually standard deviations for the inter-trial variation. I do those just using those you wouldn't get from this crude fit up here. I just said, okay, I don't know, let's try 20% as CVs for this thing. So I centered them there and put modestly large variation around that. So that, again, I start out with fairly over-dispersed values on that. And then finally for sigma, I actually do use the value that I got from the fit here. Now, because it did not consider the inter-trial variation in here, this is probably a bit oversized, but that's probably okay. Sigma is usually pretty easily fit in these problems, so even if it's not a very good initial estimate, we'll probably end up fairly okay. So I come down here, I tell it what I want to monitor, and of course I want my Emax, E0, basically our population medians, and for both of those, my ED50, and my standard deviations. In addition, I'll go ahead and collect the individual trial specific values for Emax and E0, and I'll get the two different types of predictions I talked about, our individual and population predictions. Go ahead and run Emax here. I just start out with a sort of a default here of 10,000 per 3 chains, 10,000 per chain, and 4,000. Although I'll give you a warning beforehand, with an Emax model that may not be enough because of the autocorrelation you tend to get with Emax models. Nothing special in here. This is boilerplate for a while. Going through the rest of it is the same as what we did before. Where things change a bit is when we come down to our posterior predictions. In here where we're going to plot our fits is I do two separate sets of those. One using the individual predictions. That's with this resp.cond here. And then if you scroll down, you'll see I pretty much replicate the same thing, but do it for the population predictions in here. The rest of the code here is very similar to what we did for the example I showed you before. A key difference here is that instead of a single panel, there's going to be multiple panels, one per study, and that's where this symbolism comes in, the upright bar with on the right-hand side an indicator for the studies in here. So let's go ahead and run it and see what happens. I forget how long this takes. I don't think it's too bad because it's a pretty small data set. So why don't I go ahead and just select the whole kit and caboodle here and run it. So it should go down. It should fire up our bugs in a moment. There we go. Bugs is running. Crunch, crunch, crunch. And if you want, you can actually interact with it as it's running. Yeah, it's actually running pretty quick in here. Again, it's a small data set. Boom, boom, boom. Almost done. Running a few things. There's a little bit of black there. We might want to see what it was telling us. I guess I'll wait until it gets to the bottom. Okay, it ran. Let's see what kind. I know there were a few errors up there of some kind. Let's see if they're ones that we actually care about. I suspect not. Let's see, what do we got? Okay, that's our usual errors when I've got clear WD equals true. So those are innocuous. And yep, we're fine. No problems there. Okay, so it ran. Let's see what kind of stuff it gave us. Let's go up here. Okay, let's get this out of the way for the moment. Close some of this stuff. Okay, so let's go to our dose response and come on, refresh. It didn't refresh me there. There we go. Okay. Come on, show me what's in there. There we go. Okay. So we've got some results here. Let's take a look. Start with the our diagnostic plots. Okay. So get that big enough for you to see what's going on. Okay, well, let's see what we've got here. It looks like looks like we'll have another page here, but let's see what we've got. So let's start from the bottom. Deviance I don't usually spend a lot of time paying attention to for this context. So let's take a look at ED50. It looks like we've converged to a common distribution, but there's a lot of wiggly snake stuff going here. So we've probably got a tolerable answer, but the precision might not be optimal. E0 looks pretty clean. I'm not sure why all of a sudden it spewed out a sort of an extreme value out here, but it's a little hard to tell because of the scale, but I think we're actually in pretty good shape there. Emax, too bad. Again, it's throwing out a few extreme values in some of this, but none of this is particularly worrying me. Again, it's because of the extreme values. It's hard to see the detail here, but again, there's some sort of wiggly snake stuff going here. And because, in fact, Emax and ED50 are usually pretty correlated in these things, so that's part of the reason for why, for some of what you'll see in here. In fact, maybe in a second, maybe I should illustrate that correlation for you so you can see kind of what I'm talking about on these things. Let's see here. We've got our variances actually look pretty good. Again, it occasionally throws an extreme value, but generally underneath the hood there, it looks like a fairly fuzzy caterpillar. And I guess we got actually sigma surprises me. It's actually a little messier than I would have guessed. There's a fair amount of wiggly snake stuff there. Again, I'd probably, if I needed good precision on some of these, I'd probably push this for 5 to 10 times more samples. Would be my seat of the pants guess on this. Okay, will it give us the? Okay, it has given us some Gelman-Rubin-Brooks plots here. Nothing awful. You can see for the most part, although the numbers aren't as low as I'd like to see on some of these. You can see that, let's see 1.1. Yeah. Again, I'd probably want more samples. There's no serious convergence pathologies here, but I might want more samples. You can see one consequence when you get an extreme value like we saw with the E0, that one extreme value caused a blip at the end of this, but for the most part it's actually pretty clean on that. But again, it looks like probably want to do a few more samples to get good precision on this. So this is good for sort of a draft run, but I'd probably do more for a production run. We go back to where we can look at our posteriors here. So for example, it says our ED50 seems to be sitting here down, getting pretty close to 5, must be roughly around 7 where we're centered here, but kind of going all the way from around 4 to around 8 or so here. You can see the median E0 is centered pretty heavily around 2. The reason it looks like a spike here is because of that one extreme value that it returned, which is kind of stretching things out. In here you can see our standard deviations on these things are relatively low. They're sort of 0.1-ish here, it looks like, for our inter-trial variation on our 2 parameters. For sigma, it's a bit higher, probably pushing, you can see it's going all the way from around 0.05 to about 0.3 here, centered, a little less than 0.2. I got our Emax here is centered pretty well around 10, but pretty tightly determined on this. Okay, so that gives you some first looks at your parameter values. We'll look at a table in a second to see that more detail. In fact, maybe this is a good point to look at the table. Let me move that out of the way here. Let me go ahead and open that up. And I'm looking at the wrong. It's there. We go. Let's make that bigger. Okay, so we can see. Let's see a few things going on in terms of going back to our diagnostics for convergence and that. It's worth taking a look at effective N over here. So recall we did, what did we do? We did 10,000 per chain, and we threw out the first 4. So we've got what 6,000 per chain. So the 1,800 is how many we actually. Is that right? I'm just surprised by how big some of those numbers are. Let me double check that that's actually how many I ran here. Let's go back up. And then I calculated it right. Oh, actually that's not that. Let's look at this window. It's a little easier from here. Okay, we did 10,000. Yeah, it was going to be, so it's 6,000 times 3. So, 18,000. I'm sitting here calculating wrong. I'm thinking hundreds. So So we've got 18,000 that we actually had to work with. So we can see here that, you know, I was pretty much saying I thought we were in pretty good shape for things like the E0 and for our 2 omegas, and that's correct here. You can see we're well into the thousands. It's certainly less than the 18,000, but they're pretty decent here when we're up into the, you know, into the 3,000 plus range here. But we do have some autocorrelation. You can see in our, for instance, in our Emacs, in our ED50 here, a fair amount here. So the worst one being ED50. Notice that the effective N is 158. So if we were trying to make strong inferences about ED50, we probably want a few more samples there, depending on whether we care about the mean or the tails. If we're concerned mainly about the mean, then, you know, what do we want? We probably want, you know, at least on the order of 1,000 for things like that. So that tells me right away I probably want to do at least 10 times more samples. You can see sigma 2 had shown a fair amount of autocorrelation, and that shows up in the effective N of 430. Okay, and of course all these numbers over here are means and standard deviations, and our quantiles here. You can get your credible intervals by going from the 2.5 to the 97.5 and look at those and see and make inferences based upon those. Okay, let's go back to, not there. Okay, so let's go back to our plots. Okay. Okay, and then our fitting plots. The first one here was our so-called individual prediction. So again, this would be predicting what would happen if I was to actually replicate these treatments within the same subjects and the same studies in here. And you can see the posterior medians are the blue curves. You can see the circles there for the data, and the red dash curves are 90% credible intervals then for all of our predictions here. And you can see these are fairly tight around these values. And you can see for a large study, I think 3 was our largest study. You can see those are going to be somewhat narrower, because keep in mind these are posterior predictions for sample means in this case, so they'd be more precise for larger studies. Next slide, you can see very similar pattern, except all of the credible intervals are broader, and that's because we're now talking about our population predictions, or making predictions about what would happen if we were to do a new study that had the same design as the original studies. So it includes, so this is wider because it also includes the effect of the interstudy variation as part of the spread determining these credible intervals. Okay, and I think that was pretty much the story on that I wanted to tell. So let's bring our slides back up. Okay, well, the next, I know what I promised I was going to show you. I forgot. One more thing. I was going to show you the issues around the correlation. Let's see if I can do that in a reasonably brief way. What I wanted to do is show you just an illustration of what I mean by the correlation between some of the parameters. And in particular, with things like Emacs models, you'll usually find that the correlation in the posterior distributions for things like Emacs and the ED50 tend to be fairly high. So for example, if we just do a fairly simple plot here, where I'm going to take the posterior distribution of the, I got to remember the naming we used here. Okay, it's just called, okay, it was MEDI, okay, med.emax and and just ED50 because that didn't have any inter-trial variation in it. Okay, so let's say we put med.emax and plot that against the posterior distribution for the ED50. That'll do it. Might have to change the symbols so the things don't tromp on each other too bad, but we'll try that. Let's see what kind of a mess we get. Actually, it's not as bad as I thought for this problem. I hadn't actually looked at it for this specific case. Get up there. It's actually not too bad here, but it is there. You can see, particularly when you look out at some of the extreme values at the high end here, you can see some of this out here. I'm wondering actually if we look at this in the let's try that actually if we log transform, if that what the picture looks like, because that was kind of how we originally parameterized it. Okay, where's my... Okay, yeah. It's a similar picture, but there is some correlation, though it's not as gross as I actually expected in this particular case. Probably maybe because the Emacs model was better determined than I realized from the data that I was giving you here. But it can be an issue sometimes. Okay, let's move on. I'm going to close it out here in a minute here, but I'll give you something to do in the meantime. Okay, this is all just repeating what we've already seen. And that's to assign to you what I've labeled here for our hands-on example 2. Where we're going to be looking at the population PK/PD modeling of time-matched biomarker and PK data. And actually what we're going to start with is the raw data we're working with is actually the same as from the hands-on example 1, but now we're not going to time average the data like we did in that. Now we're going to keep all of the individual data as it was so that we'll have multiple observation per individuals. So now we're going to have, in effect, separate dose response or concentration response curves for each individual as part of a population model. So we're going to take that original data. Recall again, it was a phase 1 single dose study in healthy volunteers, parallel dose escalation. There were 8 subjects per arm, and what was it, 10 arms, I believe here, placebo and several different doses of ME2. The PK measurement was plasma concentrations of parent drug, and then our biomarker was ex vivo inhibition of factor Xa inhibition, and both quantities were measured here. You can see it several times after a dose. And before, again, we had done this bit where we took the AUC up to 24 and divided by 24. Not now. We're going to keep all the individual time points intact and analyze that. So we're going to be applying a direct action PK/PD model to the time-matched factor Xa inhibition and Me2 plasma concentrations. You've seen this before too, so this is just showing you the data. First is time courses, so I'm plotting the plasma concentration of drug versus time for all the different treatment arms, and then doing the same for the factor Xa inhibition, looking at those. Now again, they were all measured at the same time, so we can create data. We can create these data pairs where we look at the plasma concentration versus the factor Xa inhibition, or actually the other way around. And that's what we're looking at here. So we're looking at factor Xa inhibition versus our plasma concentrations, and you can see those as we go up here. I changed the x-axis scale is different all the way up here. You can see it's broader as the dose goes up, and you can see a pretty well characterization of the shape especially as we get to the higher doses. And also here I've just thrown all the data in one single plot here. I'm just throwing it up here so you can sort of get a general sense of what the shape is, so you can kind of see that sort of Emacs-ish looking thing that seems to be going on there. So that's what we're going to be modeling, but now we're going to model it as a population model where we allow for inter-individual variation in some of the parameters, and we're going to start and keep it simple. We're just going to do it in one of the parameters. So we're going to do a sigmoid Emacs model. It's going to relate our factor 10A inhibition to our plasma concentration. Here are the indexes. Here we've got I for occasion and J for subject. So here our response in the on the ith occasion and the J subject, it's going to have a normal distribution for our residual variation. Our mean effect here is going to be our sigmoid Emacs model, no intercept. And then we're going to allow for inter-individual variation in EC50. And here, thus there's a subscript J on the EC50. So that's what we've got right here, and that's going to be log normal inter-individual variation on that. And then we've got some weakly informative priors on the whole mess here. So Emacs I've bounded between 0 and 1 with a uniform distribution. Log normal for EC50 hat. Or in other words, EC50 hat is our sort of typical value for the population there. Our gamma will put between 0 and 10, again a uniform, and then I'll use a pair of uniforms here for EC50 and sigma. Pick values that make them weakly informative. So let's see, so that's going to be your task. The resources for that is we've got there's a folder in there called ME2 Hands-On 2. There's a data set, fxadata.csv. Now the model, there's a model and an R script already worked out for you on that. Actually, there's also an alternative model here that we won't worry about right now. It's just basically asking, well, what would happen if you knew or strongly believed that the Emacs was 100? What would happen? But we'll talk about that one later. I'm actually trying to decide how best to do the tasks on this for the coming session. The way I would recommend doing this is actually, now these are really solutions. I'd actually recommend that you try and figure them out on your own. And in particular, the way I would start would be to first try writing the model itself for this case. So I would, maybe either save these someplace or whatever, but rename them or whatever, and don't look at them would be my recommendation, and go ahead and try and build the model from scratch. But you can use dose response 1 as something of a template to help you out with it. So that's how I would attack that. And similarly, once you think you've got that in hand, then go ahead and try and do the same for the R script. Again, I would go and you maybe use the dose response 1 example as the template to begin with for that. And then we'll spend time going over that in our next session. We might even end up with the hands-on 2. We might actually end up covering this one in 2 lab sessions in order to get all the elements, because there's some additional things that after you get sort of the basic R script down, there's some additional add-ons I'll show you about that will affect both what the model looks like as well as the data. I'm sorry, as well as the R script here. So anticipate the answer, sort of the lab sessions on here. We'll probably go over a couple of sessions on this one. So, but I would focus most between now and our next session here, probably on the on the bugs model mostly, but also go, if you have time, go ahead and attack the R script too, and try to get that running all together on that. So let's see, is there anything else? No. I think that's where I will leave you anyway until I get back from Switzerland. Goodbye till then.